Hey, Jessica. Hey, Kirsten right there. Hey, Raj V. Hey, KP. Hey, Isabel. How's everyone doing this morning? Oh my gosh, it is Friday. Friday, we're going to get some work done. Isabel, good to see you here. William, good to see you here. What are we going to do? Michelle, good to see you here. Mubot is now awake, so that means some points are in the chat. Daniel, good to see you here. Sierra, good to see you here. What are we going to do? What is the work for today? Can we go over lift and support again to get more practice? Yeah, let's do that. Let's load up the grocery data. Do it. Okay. I think I've got the notes still up. I've got this. We need to load the grocery data. Let's load the grocery data. Some lift. Cooper, good to see you here. We have lift and support BAS for. There's no music data under the assignment. Oh, let's go grab that. BAS for 74, lift and support. Let's fix that. 2 seconds under data mining. Should have the groceries. And let's make sure the music data's here. You're the first person to tell me there's no data. Insert a media, course media, user files. Maybe that'll do it. Ooh. Course files. Really? All. They make adding things so weird. It is just so weird. You have to like search. Here we go. There we go. Okay, now let's make it really big. Boom. Okay. Tell me, KP, you should see it now. I think it was KP asked about that. Could you work on Lab 5, 1, and 2? Yeah, let's look at some Lab 5, 1, and 2, which I think uses the music data too. We're going to look over some lift and support here in a second. Let's see right here. Let me get the groceries data up. There we got the groceries data loading in. Let me clear out my global environment. We're gonna look at some lift and support and interpretations in the grocery data right here. So 2 seconds. We're gonna jump into it. KP, thank you so much. Another 100 points. Sorry about that. I get the assignment going, get it written, and then we don't have the data. We need data. Here we go. Let's head over to the main screen. Let's do this. Okay. We'll do some lab here in a moment. The groceries data is somewhat used in the lab, and I think the music data too. Now, transaction data is a little bit weird of data. That's why there's no data cleaning this time. They actually gave you good-looking data. So if you go and you look at the head of the data, what does this mean? This is grocery data. Tell me about this right here. Can you interpret what this means? This is transaction data. So what does this mean? What does 3 whole milk mean? What does that mean? Does anyone know? I'll give it a moment more. I want you to think over what that means. What does 3 whole milk mean? Or 7 rolls buns? What does this mean? What is all this right here? This is market basket data, transaction data. Even an I don't know is a good answer. Even I have no clue. What does it mean? Not the category and position. Shreya, 500 points. I like that right there. Not the combo. Good guesses. And Shreya taking a good guess right there. So what this specific kind of data frame is it's transaction data. Transaction data is individual transactions, as in person 3 came in and bought only whole milk. Person 6 came in and bought abrasive cleaner, butter, rice, whole milk, and yogurt. So that's their cart. Like they're walking around in our little mini mart with these items in their basket. Like that's what they end up buying at the end of it. It's not like they have this and then they get more. That's what they have. So this is another person right here in the grocery store, person 8, who bought these items. So we don't have tracks like if they come back, but this is a transaction that we have right here. So person or transaction number 8 or person number 8, they might be another person later in the data frame. It'd be good if we could analyze like multiple business from a customer, but this transaction data set doesn't have that availability. But does that make more sense right here if we go and look at like we go to the data frame and we go to inspect, we should be able to go, once you do inspect, woo, you get a bunch of stuff. So this is every single transaction. So what do you notice about this right here? What do you notice about this? That's interesting. It didn't reach a max print. But there are, it looks like 9,835. But then it says 9898. So, morning, Arthur. Good to see you here. Too many customers. Too many customers. We got a, I think a length of G right here. Huh. What is this? There's 6 right there. So there were 9,836 transactions. Let's look at item frequency. What does this mean? So so we know what this is. Transaction data. What does that mean? Let's round this. What does this mean? Kind of, KP, you're right. Yeah, exactly. Go into a little more detail because that's basically it. So interpret what 0.17 soda means. What does that mean? What does 0.17 soda mean? Give it a moment more. What does 0.17 soda mean? What does that tell us? 17% of customers bought soda. Exactly, Kirsten. Great job right there. 17% of customers bought soda. We can just take this right here and multiply it by 100 and see the percentages right here. A lot of people are buying whole milk. Even better yet, we could go to this table and sort it. And let's do decreasing equals true. And now we can see the most likely bought items, or we could go to the top table, right? Top 20. Here's the top 20 items. The top 20 items at our grocery store would be whole milk with 26% buying it. Now, if you notice, it adds up to more than 100% because this is not just like what is bought. It's what percent of carts have this item in there. So 17% of carts have soda in it. We might want a few more decimals, so we might do that right there. And we see better 17.44% of carts have soda in it. 19.35% of carts have other vegetables in it. And this is like when you walk around the grocery store, if you look in someone's cart, there's basically a 13.59% probability it would have yogurt in it. So really good to see what we're seeing right here. And let's also do the following. Let's go right here and go item frequency plot. And now we can see, whoa, a little bit too crazy. Little bit too much. What is the argument? I thought it was top. Is it not top? Quick question for Inspect G as it is counting 0 to... Oh, it is? Whoa. Is it... There are... It says there's 9,835 and I don't know why this right here. Like, I'll tell you when I don't know things. I'm just like, it says there's 9,835 carts. Like, the length of G is the amount of carts. And it made sense when we printed the whole crazy big long thing. Yeah, I don't know why. Well, there's no cart 0. So if you go to the head of it, there is no cart 0. There's a cart 1. And then the tail of it, well, it's because we did that. If we just go to Inspect G, it's going to take a moment. There's 9,835 carts, as confirmed by this. I don't know why that says that. I don't know why. Sometimes I don't know an answer, and I'm like, well, it says this, but maybe it just gets the next cart ready. But there are 9,835 carts. That number's there also, and we can confirm by looking at the inspect, and we can see cart 9,835 because that's what that represents. So maybe it just initializes the next cart. Like, maybe that's how it works. I don't know. It's a really good question. The item frequency plot, we can make it look a little bit nicer right here. What? There we go. It is right here, top N. There it is. Oh, you can change all these. There's lots of things you can change. Horizontal, we don't do that too. Okay. Top. No, it's top N. That's weird. I hate when things don't have autocomplete. Horizontal. Really? No autocomplete. There we go. And we can see here the top 10 items at our grocery store pretty nice and easily. So here's the top 10 items. People are buying whole milk, other vegetables, rolls and buns and soda and yogurts and bottled water and root vegetables. So you can see milk really jumps out here, and then you got your top 3-ish. Well, I mean 2 through 4. But then you've got right here another one, and then you kind of get a steady decline. We could take a better look at the steady decline by going to top 20, and yet it really is like top 1, another 3, another 1, and then a steady decline downward. Just understanding what's going on with the items bought at our store. So we might pick something that is not sold nearly as much, like we could talk about brown bread. Maybe we want to sell more brown bread, or I'll do brown bread. Nah, newspapers. We got a great margin on newspapers. Let's try to sell some newspapers. So if we're trying to sell newspapers, we might want to find things that are what with the sale of a newspaper. So if we're trying to sell newspapers, we might try to find things that are what with the sales of a newspaper. If we're trying to sell newspapers, we might try to find things that are what with the sales of a newspaper. Associated. Wow, Shreya, that's worth another 500 points. That literally, it's like, I know you're not in the class right now, but that was literally the theme of what we kept talking about. And if you look right here, yesterday during class, I was underlining multiple times talking about we were trying to find things. I said it one time. Where did I say it? I said it like 2 or 3 times. Associated. We kept talking about associations. So, yep, that's what we're going to do is we're going to talk about something that's associated. And great job, KP, there also. So we're going to work on finding these associations in the data. This is just the theory behind everything we're doing right here. And let's go ahead and grab there's transaction data. We don't really need to make subsets. We need to get to the association part of this. So let's go ahead and run the a priori learning method. Now, the a priori learning method, So basically, we learn about our data, load your data, learn about your data, and then create rules via a priori learning. Now, the reason we do the a priori learning method, even I cheat a little bit to get the code in here because it's a longer code. And let's talk about what it does. The reason we use this is to not have an insane amount of rules. Beautiful. Okay. So the a priori learning method right here is going to take, this is yes. Oh, yes, KP. Definitely. So the a priori learning method right here is going to take your transaction data. So this G right here is what we stored in as transaction data. So you have to have transaction data to do this. Next, we create a list of parameters that we're going to make rules by. Now, support is the support of an item. And what does this mean? That any item we look at must be sold at least what? Any item we look at must be sold at least what? Any item we look at must be sold at least what? Maybe not once, but at least 1 in 1,000 times. So the cutoff would be right here. Does that make sense that these items would not be considered? Any item we look at to consider for a rule must be sold at least 1 in 1,000 times. Does that make sense? These items right here, like makeup remover, is sold less than 1 in 1,000 because that's 10, 100, 1,000, and this is sold less than 1 in 1,000 times. So is toilet cleaner, so are bags. All these things right here are sold less than 1. Frozen chicken, I'd think frozen chicken sold quite often, but apparently not here. It's a special kind of frozen chicken. But we could increase the support right here. So now anything we look at, either in a combination, like the rule itself, or the items itself, have to be sold at least what? Anything we look at now to consider for a rule has to be sold at least what? Anything we look at here must be sold at least what? Anything we look at here must be sold at least what? 1 in 100 times. Great job. Peaks right there. Well, you wouldn't. Well, no, that wouldn't be the top 50. That would be something that is in. So if you did right here this, that would mean a song has to be what? How would you look at the top 50 songs? Do we have a code to figure out what the top 50 songs are? What code do we have? Good to hear Meath and William and Cooper and Reagan. What code do we have to look at the top like 50 of something? What code do we have to know what the top just general listening to? We can look at head and then we have to run what? So what code gets us the frequency of the items? So this just tells you the frequency right here of the items. And you can look at a frequency plot of it. It's too big for the screen. The top 50 via frequency plot would be too much, but we could look at the top 50 right here and look at the top 50 items sold at our store. And you can see these are the top 50 items sold at the store. Does that make sense, KP? So this lets us understand the top 50 items and the percent they are. Like hygiene articles are sold 3.29% of the time. UHT milk is sold 3.35% of the time. So this is how we could look at the top 50. Now, when you think about this, this applies down here as the following. If we put in 0.50, will we make any rules? Yes or no? So milk is sold to 25% of customers. If we put in 0.50 as our support, our minimum support, will we make any rules? No, because only things with at least 50% support would make a rule. So we can't. We could try to put in 25, but then it's also the rule itself needs that much support. So we can't even do that because it's just going to be like, you're not going to get any rules. So you have to watch out putting this really high because even at 25, I don't think we're going to get anything. It's going to say rule of 0 or so, set of 0 rules. So you're not going to get anything. Probably even 20, a little, I don't even think there. 0 rules. So you see, you can't put it crazy high. 0 rules. Now we'll get something. Don't fail me now. 0 rules. Wow. Sorry, I get worried. Hey, we got rules. Can't put it too high. Got a little worried on that last one. I was like, something going on here. Okay, so what is the confidence? Confidence is saying that's probably what was holding us back. What does confidence tell us? Yeah, confidence was holding us back. What does confidence tell us? Anyone know what confidence is? What is confidence? I adjusted the confidence and I brought it down. So what is confidence? Confidence means if somebody does the left-hand side, what is the probability of the right-hand side? Like if somebody buys rice and sugar, then what is the probability they buy whole milk? So what would this mean right here? Just try to interpret it, because this is what you'll be doing on your assignment. We have rice, sugar. So if somebody buys rice and sugar, then what does that mean for the probability of them buying whole milk? 100% of the time, if somebody buys rice and sugar, then 100% of the time they'll buy whole milk. That's what the confidence means. So the reason you're saying these parameters right here is you're saying, when I get this returned to me, I must have at least this much confidence. Does that make sense right there? So we can then take and we can sort our rules. Let's go grab a code like this right here. Pretty code. Let's go here and look at our rules. They're using a quality of the rules. They need to lift at least this, so they're even subsetting down further. And let's see, can we do that? That might be a little iffy. Oh, it did run. It just like did the weird thing. And we're putting import, and then we need to inspect that. Probably going to get nothing. I think that's got nothing right there. Dun, dun, dun. Nothing. Yeah. You just inspect the rules. So, KP, is this making sense? Let me know if I'm saying anything that's not making sense. Let's inspect our rules. There we go. There we go. We got too many rules. so much. We can sort this too. Actually, one of the easiest ways to sort this, I think we can capture that. Yep, we did. Okay. What is the lift over here? Because I think this was your first kind of general question. What does that lift mean right there? So what does this lift mean right here? Which is kind of neat. Or pip fruit was something we might want to sell too. Kind of makes sense though. What does the lift mean? What does the lift mean? So what does this value mean right here? Or silence. No. Maybe things we were selling with it. No, Shreya, good guesses. Good guesses. So the lift means if somebody buys other fruit and whole milk, I think Kirsten's got it right there. If someone buys other vegetables and whole milk, they are 2.84 times more likely to buy root vegetables. Yep. So what you can do right here is you could test your knowledge. Here's this right here. There we go. We need to grab that. And I'm losing it. And this is the delifting. And what was the item again? It was, I think you'll have it also. Great job, Riley and KP. Root vegetables. Should be able to do respect G. Root vegetables. Oh, no. And take a look right here. What is this formula right here? What are the values I'm dividing? To get the original item frequency, which you see right here, what values am I dividing? To get the original item frequency, I'm dividing the this by the this, which is some terms we were talking about. And I think KP, great job right there. So what have I divided? Yep. It's not confidence divided by original. It wouldn't be confidence divided by original. It would be the confidence divided by the, because that can't be a probability. So that is impossible to be a probability. So that's the confidence divided by the what equals the what? The lift. This is the lift equals support of item. So the confidence divided by the lift equals the support of the item, because right here, the item frequency of root vegetables is the, no worries, KP and Reagan, good work right there. And also Isabel, good to see you. So the confidence divided by the lift equals the support of the item. So is this making more sense right here? And then we're just creating this right here, verbose false, just stops it from doing a bunch of output. There's a bunch of verbose iter and stuff that stops a bunch of output from displaying on the screen. These are just ways you're setting up your rules to be such that you're saying, I want to have at least a support of 0.01. I want to have at least a confidence of 0.01. Now, the problem with doing this right here is we really didn't narrow down the a priori method, and we got 522 rules. We go even crazier. And you can't do a list of rule 1. And now it's taking a little bit longer. This is the point of the a priori learning method. The point of the a priori... Oh, no worries. That's fine. That's your practice. Everyone knows how long this is taking right here to run. This is what you don't want. And this is why we do the a priori learning method, to not have it run this long. When you do the a priori learning method, what you're doing is you're saying if a rule does not have certain requirements, or it's not a rule, well, rules too. If an item or a rule, like you have rules of two things, like left-hand side, right-hand side, two things, right-hand side, one thing. If something does not have enough support or does not have enough confidence, it gets removed from being looked at later on. So because of that, we're eliminating some of the millions, if not billions, of combinations. And when I say billions, I'm not joking. There are quintillions, quadrillions. There's quadrillions of combinations. There's so many different ways things can be done, and R is still thinking. We'll try to let it finish this thought experiment right here. But if you don't use the a priori learning method to look at rules, you have this happen right here where you can't look at all of them. So what do? You narrow down your scope. You say, I want there to be at least this amount of support. I want there to be at least this amount of confidence. I want there to be a length of 2. I want there to be a length of 4. I want between a length of 2 and 4. So this method right here, where we try to minimize the amount of stuff we look at, is going to save us from this nightmare over here where R just says, like, I am confused. R is using 9 gigabytes of memory right now. Does everyone see that? This might be bad. R is currently using 9 gigs of memory. When it's using 11. Oh gosh, we need to stop this. Stop. R used. Wow. Did we get any rules? Woo! I have no idea. That is memory in use 82%. Oh my gosh, what have we done? What have we done? That was bad. We don't like that. Can I think my RAM is screaming right now. And that's why we don't do this. That's why we do this. Oh, I deleted G. What are people's thoughts? And my computer literally just started spinning up right there. Now that ran, everything right here. We won't do the importance. What are people's thoughts? Null, we got no rules. Oh wait, it's still stored last time. How did it store and then not store? Inspect like prints to the screen. I don't know why it's not storing this time. Now it does it. Maybe you have to run it twice. No, it's doing it. That's weird. What are people's thoughts about rules and what we're learning from this data? What are people's thoughts? We can also narrow down left-hand side, right-hand side. Make rules about beer, make rules about yogurt. Let's do one of those real quick, and let's narrow down and only look at a certain subset. So we need to tell it to only give us the left-hand side. So we can sort the rules by lift. I want a, there we go. Here it is. So we want a subset, left-hand side has contained in it this. Either which one works, and let's store this right here. So this is where we're specifying what must be in the left-hand side, but I want to do right-hand side instead. Right-hand side is what we are trying to have people buy. So let's say we want to have people buy newspapers. Was it newspapers? And let's see. Object newspapers not found. Was it newspapers? Item frequency. What are people's thoughts? I thought we had newspapers in here. Item frequency of G. Turn newspaper. Nope. There we go. There's newspapers. And we didn't spell it right. Newspapers. Okay. We have 8 rules. We have 8 ways to sell people newspapers, our big margin thing. Let's go ahead and inspect these rules. And there's the rules. What do I see? Which of these is going to be the best at selling people newspapers? Rule 1 through 8. Which of these rules, take a moment right here, if this was a test question. Which of these rules will be the best at selling people newspapers? I guess you could come up with other theories. But I have one I would pick, and you have to give your reasoning. Which of these is the best at selling people newspapers? Rule 1 through 8. Rule 2, and you got it. Why Rule 2? Great job, KP. Why Rule 2? That is the one I would pick also. Why? Great job, Joseph. And why is it Rule 2? I think people are noticing. Why is it Rule 2? Not the wait, let me see. Yeah, it would be the confidence. Yeah, you can look at the confidence, or you can look at the lift. My brain broke for a second. Yeah, the lift. The lift and the confidence are going to be, like, if lift goes up, confidence also goes up, because the right-hand side's always newspaper here. So if you have the same right-hand side, then higher lift means higher raise to the initial probability. What is the initial probability we sell someone a newspaper? What is the original probability we sell someone a newspaper? Try to figure that out right now. There's about 16 ways to figure it. No, maybe 8 ways. What is the original probability we sell someone a newspaper? Maybe around 8% or something. Yeah, it's gonna be it's gonna be close to 8%. But try to find it like it's a test question. What is it? Let's see if people get it. What is the original probability? We were covering this earlier. If you have more questions, let me know. 201, 474, 475. Let me know your questions. What is the initial probability we sell someone a newspaper? The original supportive newspaper. What is the original supportive newspaper? So how would we get that from this table? If we know its new probability, and we know how much it's been increased from its original probability, what could we do? So if we know its new probability after the rule, like if someone buys bottled water, the probability they buy a newspaper is 10.211. So what could we do to the new probability? So if you look, one of the easiest ones to look at, great job, Kirsten, right there. Look at this one right here, and what do you notice the lift is very close to? That's how I looked at that, and I was like, yeah, it's going to be close to 8. Because that lift right there is one of the least significant lifts you can look at. We can look at is significance of the rules also, but that's one of the least significant lifts there is. And since that lift is so insignificant, it's close to 1. That means if we were to take this probability right here, divide it by the lift, it's going to stay about the same, because if you divide something by 1, it stays the same, and it's basically 8%. Then we could confirm our answer right here by going to item frequency and put in the data set and do newspapers. And it's the same answer, just rounding there at the end. Lift is the highest, exactly, peaks right there. So making our decision about the highest lift, but you also might want to look at something like, someone might say, well, whole milk, because this applies to a lot of people. So if you notice the support right here, someone could say a lot of people buy whole milk and newspapers. This applies to 2.7% of our customers. So maybe we get more people to buy whole milk, but we already know from the original thing that whole milk is bought something like 25% of the time. So I might look at some of the other, like whole milk, there it is, 25%. But things like the tropical fruit are not bought that often. I don't know why. Maybe the tropical fruit stand is near the newspaper stand, but tropical fruit, well, it's bought 10.5% of the time. And we're pretty popular on that tropical fruit. But that's the left-hand side. And that should be, because I don't use this one that often, this value right here is the coverage. So the coverage is the left-hand side support. Not a big fan of coverage. I just don't use it much. All it is left-hand side support. If your rules are longer, though, do we not allow for rules of length? Oh, we did. We did some craziness over here. Where did we lose the rules? I don't want it to break. Okay, that ran. That ran. Okay, now let's take a look. Whoa. Take a look. Now we have 10,000 rules. What do we have to stop this from happening with 10,000 rules? Remember I said we can get a lot of rules? 10,000 rules. Which, frankly, we can do this. What do we have to stop this? Do we subset the newspaper rules? We have the a priori learning method. Let's go look at the newspaper rules. Ooh. If you notice here, the support is really low, though. This only applies to 23 customers. Can you look at the bank loan question? Oh, let's do that next. You got Jessica. Thank you so much for asking. We'll do it here in 3 minutes or so. These don't apply to that many people because these have very low what. Like, I really lowered down the what so we could see this last question right here. I really lowered down the what. So this doesn't apply to that many customers. So I don't know if this rule would really be good. We could run some is significant on this. I don't know if this would be a good idea to like make a like buy chocolate buns and buns, buy chocolate and rolls buns and get a discount on a newspaper. So we might try to, or maybe like buy a newspaper and get chocolate. I don't know about a newspaper. I don't know about that. I really lowered down the support. And what would make us really confident? Oh, that's because they have the highest lift, of course. Napkins, rolls, buns. It's a lot of, I don't know. It's hard to say the marketing strategy here. But we really lowered down the support on this. So that's why we have so many more rules, because we're allowing more rules because people don't have to have a high amount to be part of this list. Here's once again our whole milk and newspapers, and that applies to 269 individuals bought whole milk and newspapers. Well, let me know if you have more questions. This is a good start on your assignment. Let's head back to the main screen. Awesome work, everybody. Let's see. Lots of great stuff. Starting out some music. Let's start up the, is it the bank loans? Did you say? Can we do the bank loan question of chapter 13 homework? Yes. Bank loans question. Okay, chapter 13 homework. Bank loans is going to be, that's the distributions. That's the, that is a people paying back their bank loans. So that is probability distributions. The sampling distribution of the true proportion. I couldn't think of it. Okay. Here we go. I think we found the bank loans. Chapter 13, bank loans. Let's take a note on it. And we're here at 39:55, Stat 201, Chapter 13, bank loans. Let's go check it out. Here we go. Okay, so the number one thing that you need to know in Stat 201 is know your notation. Can someone put that in the chat for 100 points? You have to know the notation. You have to know the notation. You have to know the notation. We're going to review it coming up here in a second, but you have to know your notation. You have to know it. And we're going to talk about what it means to know your notation after we open up Photoshop here in a second. But you have to know that notation for 100 points right there. Know your notation. Go away, Photoshop. And so let's know our notation. Okay, great job right there, Reagan. Let's go over here to Microsoft Word. And let's drop in the work. Okay, so it's asking mu p hat. Now, mu p hat sounds like it's an equation, but it's not. Mu p hat is a value. And what you actually have right here is in this chapter, if we meet the conditions, the data will be normally distributed with a mean of mu p hat and a standard deviation of SD p hat. Now, we usually don't call them by these names. Usually they go by the names of normally distributed with a mean of p and a standard deviation of p times q over n square root. So we have here that this is the mean of the distribution. That's all that says. It says the mean of the distribution of the sampling, the mean of the sampling distribution for p hat, the mean of the sampling distribution for p hat, and the standard deviation of the sampling distribution of p hat. And these quantities are equal to the mean of the sampling distribution of p hat is equal to p, and the standard deviation of the distribution for p hat is equal to p times q over n square root. So an important thing to ask is, we probably need to know a certain value. What value do you think is super important to solve both these equations? We want to know what mu p hat is, and it's p. We want to know what SDP hat is, and it's p times square root and square root. Jessica, 100 points right there. We want to know p. And p is the true proportion. A bank believes that 7% of their customers won't pay back their loans on time. That makes this p equals 0.70. Now, what is q? If we know p, we can find q like that. So if you know how to find q, go ahead and tell me, like, what is q? Q is 1 minus p. So if p is 0.07, q would be what? So just think 1 minus p. What is q equal? 0.93. There we go. And that is what q is equal to. So we have p, we have q, and we can basically solve this. One last thing we need to know is what? We have p, we have q. Now we need to know what? We almost have everything. We have p, we have q, and then we're one step away right now. N. And it says here they're going to do 400 loans. There we go. So let's go ahead and solve. So remember, we're just going to go p is equal to p. And the way this works is, let me ask you this question. If a bank believes that 7% of people won't pay their loans back on time and they give out loans, what percent of loans would they not be what percent of loans would they expect to not be paid back on time? Now, don't go too complex. Just remember, a bank believes 7% of people won't pay back loans. They give out loans, what percent do you think would not be paid back on time? That's what this means when you think about it conceptually. Like, a bank believes 7% of loans won't be paid back on time. What percent would they expect to not be paid back on time? If they believe 7%, then what would they expect to see? They're like, well, we think 7% don't get paid back on time. So they'd expect to see, when they give out loans, what would they expect? They'd expect, and that's why we put it at the center of the distribution. If they believe 7% won't be paid back on time, they'd expect what? Don't go complex. They'll probably see about that, right? So it's not that, and Jessica, does that make sense? Like, it's not that they will see that. It's that that's the most likely thing. That's why it's the mean of the distribution. If 7% are not paid back on time, generally when we give out loans, then we'd expect around 7%. Why? That makes it the center of the distribution. Yep. So it's like, well, that's the most likely thing. But then there's some variation in what occurs. And the variation, put two letters, S something. The variation in what occurs, or what could occur, is the what of the distribution, because we won't always see like 7%, 7%, 7%, 7%, 7%, 7%. There's variation in this, and the variation is known as the what of the distribution. The variation is known as the what of the distribution. Because we won't always, it won't be like we give out loans and 7% is how much is not paid back every time, or 7% of people don't pay back their loans. There'll be variation. Sometimes it'll be 8%. Sometimes it'll be 6% people don't pay back. There'll be variation, and that variation is known as the standard deviation. One click away, I missed it. P times Q over N square root. And that's basically equal to 0.013. So go right here. Does that make sense right there, Jessica? That the standard deviation, we have a mean of 0.07. We have a standard deviation of 0.013. And so that's the unit increase or decrease that spreads out the curve to say, like, we expect generally, if we think about two standard deviations, which is a z-score of 2 and -2, we expect, generally speaking, about 4.4% to 9.6% to not pay back. It makes part C awesome. Well, now we're going to need, for later in the question, some David M. Lane to help out with this. And we're going to remember these numbers and remember the number we got in our calculator for the standard deviation with the decimals. Let's go look at the question. Okay, so the mean of the distribution is 0.07. That's the mean. And the standard deviation of the distribution is that 3 decimals There we go. And then the conditions, we have to randomly give loans. So we have to randomly give them out, less than 10% of the population. And then we have to have at least 10 successes, at least 10 failures, which would expect 28 people to not pay back their loans on time. 7% times 400 is 28. So we have at least 10 successes, at least 10 failures. And with reasonable assumptions, the conditions are met. We go into greater detail on conditions, but something we check for each question. A little quick on those. Now we get to part C. Okay. Part C right here, we just got to think really hard on it. We got to be like, boop, boop, boop. Think really, really hard. Is how to solve it. So really, this is actually a tough one for me to think through. No. And then we'll show the real way to solve it. There we go. Okay, let's talk about how we got this. Okay. You're not meant to solve it that way. Here's how you're meant to solve it. You can go to the David M. Lane applet. And on the David M. Lane applet, which the link is in the chat right there. So go to the David M. Lane applet. And on the David M. Lane applet, you need to enter in your what and your what on this. You need to enter in your what and your what on this. On the David M. Lane applet, you need to enter in your what and your what. On the David M. Lane applet, you need to enter in your what and your what. The mean and standard deviation. Yep. And there's that. And now we want to graph and look. Wait. And this is why, if you're wondering how was Brian able to solve it, I had drawn the picture already and I was thinking about the picture. So look at the picture I have on the screen over here and look at what I have drawn out from working the problem earlier. If you're like, wait, how did you do that in your head? Well, I use this picture as a reference, and then we are plotting above right there. So now we need to make this picture look like this because it says greater than 9%. So we go to above 0.09, and there's the exact answer. It was actually very nice to me. Shocked I got it because my answer is a little further off than I would have thought I was, and somehow it gave me the answer. So it looks like it has a decent margin of error on that answer. If you notice, my curve isn't as asymptotic as theirs is. I need to get better at drawing my normal curves. But it still is in the same spot-ish, though. It's still a close between a z-score of 1 and 2, 0 z-score, 1 z-score, 2 z-score, somewhere between 1 and 2. And that's what I was estimating in my head because I know a lot of the percentiles on the normal curve. And I was trying to think, okay, where is this at? Okay, it's probably about 6, 7%. And my guess of about 6% was kind of close because I went to 7% first. You're not meant to guess it. You're meant to use the David M. Lane, but you should have a decent understanding. And I always suggest drawing it out. If you can draw these things out, that pretty much would answer any sort of question we could ask you on the test, because sometimes we give you the pictures on the test and we ask you to understand what you're seeing. Does that make sense, Jessica? And were you able to get your question? Let me know if you can't get yours. I could put in the numbers, but the David M. Lane is going to solve the question for you. But also, people say, well, I won't have that on the test. I do want you to have the understanding of drawing it out. Hence why I usually go and find my mean and standard deviation and then draw the curve and then try to draw a picture. This is probably one of the best ways to make sure you understand it, because when you draw this picture, if you have the picture drawn, then you go over here and you draw it with the applet. Awesome. Do you want to do another one? I love doing these. I like taking the guesses on them. I've been solving these questions for like a decade. So I'd say around year 5, I was able to solve it without the applet. It took 5 years, but then I could start solving these without the applet. I was like, oh yeah, okay, this. Like I've solved this question a good 100 times maybe. So yeah, maybe I'll be able to start solving it without the applet now. Well, thank you. I appreciate that. Just 10 years of solving a Mike Pearson problem on stats. So hopefully you improve, right? I'm one of those people who's always like challenging myself to try to do better. So if I don't use the applet, I think it's fun. So just kind of having an understanding of how the curve works. I think, is there the waiter waitress question? This is the school budget. Have you done the school budget one? We could do this one next. Did we do this one? No, this one's tricky. What is the probability it'll lead to defeat? So haven't done it yet. I'm trying to see if I can solve this one quickly in my head. Thinking about it real quick. Okay. It's got to be. This is a very hard one to guess. This is a very hard one to guess. I don't even have the quantities. I can probably get a better guess once I get some quantities. Okay, going off of how we did the last one, what do you think the first thing we're going to do right here is? What do you think the very first thing we're going to do on any sort of problem like this is? Here, let me mark this as school budget problem. What do you think the very first thing we will do on any problem we get is? So this is Stat Tool 1, Chapter 13, school budget. What is the very first thing? Great job. Jessica's saying, find that notation. 100 points, Jessica. That's exactly it. We're going to start finding that notation. And for these problems, P is a notation we need to find. So if you look right here, what is P? It says, suppose that 53% are going to vote for it. That is P. Now that we know P, we're going to find Q. Q is the complement of P, and that is equal to 0.47. Now, there's one last quantity. Great job, Cooper. Also, another 100 points, Cooper. What is, and Cooper's already ready to go on the next on Q. What is the other notation value you see here? And then there's a secret notation value. What is the other notation value you see here? And then I'll tell you the secret one. So there's N. Great job. Yes. Nice job. That is how many people they're going to poll right here. Now, with this, here's the big one. The secret one, you could find X, but the actual secret one is this. This is P hat. If something were, and I guess we could write prob P hat, I could do less than 50%. Because if something were to be predicted to be defeated, then in a sample, we would see less than 50% of people voted for it. Imagine if you talk to 100 people and you say, are you going to vote Brian Stevens to be governor of Tennessee? And 0 say, I'm going to vote for him. So what's your best guess of the percent of people who are voting Brian? Don't vote for me for governor. Don't do that. So they're on the right track on what they should be doing. But what would be your best guess? You talk to 100 people, 0 said they're voting for Brian. So your best guess is what? Your best guess would be what? 0 votes. Hey, Charlie. Good to see you, Charlie. So what would be your best guess of the percent of people who are going to vote for Brian? You'd be like, no one's going to vote for him, right? But let's say we live in some weird alternate reality where Brian became a politician. We don't want to live in that alternate reality. And 80 out of 100. What is your best guess of the percent of people who would now vote for Brian in this alternate reality? What's your best guess in this alternate reality of you talk to 100 people, 80 say they're voting for him. So, and you could just call it Candidates if you want, 80%, right? So when we go and talk to this sample, the sample is going to give us a guess at reality. Now, this is what's weird about this chapter. The really weird thing about this chapter is we know the what right now. This is just weird about it. We know the what, because this is the only way to do sampling distributions is to know the this. So the only way to do these chapters, which this really works well for manufacturing, in manufacturing, they might know the this. They know right now, it says that you know the truth. Does that make sense? You actually know somehow that 53%, it says, suppose the budget has the support of 53%. So that's the truth. That makes that P. So the reason it's P, it's for some reason, which doesn't really make sense theoretically, you know that 53% of people are going to vote for this. So you'd say, well, why would you do a poll? I don't know. It's my Pearson problem that it makes more sense when you talk about the nearsightedness. We have data to know that maybe 10% of kids are nearsighted. So it's okay, then what would we expect if we take a sample of 200 kids? What would be the expected amount of nearsighted children? So that makes more sense if we have very good historic data. I guess you could do, if you're doing political stuff, you could say historically this, district shows 53% support for initiatives. What would we expect? It should maybe say that, rewording it. They're using the sample to make assumptions for the population. No, it's the reverse. That's what's weird. This one's the reverse, Charlie, 100 points. This is using the population to ask what we might see in the sample. In almost all instances, statistics go, you use a statistic to make an insight into the population parameter. But in this one, we're using the population parameter to make insights into what we might see in a sample. So that's why we call it sampling distributions, because it's what is the theoretical sampling distribution from a known population. So it's weird. It's used in industry to say, like, if you have, like, let's say you have defects. So you know that your population has a defect of 2%. So what percent of defects would you expect when you send it to someone? You know, and you're going to send someone like a bunch of bolts, and 2% of your bolts are defective. That person should expect to get what percent defective bolts? You know that 2% of your bolts are defective. Like we say we got a lot of data on this. Silly in my own. Well, so this is we're going to send them a sample of our bolts, right? I'm going to send this person 100 bolts, or let's go 500. We're sending lots of bolts. What percent of their bolts should be expected? And we could tell them this. We could say, we expect this percent of your bolts to be defective. Like, you're probably going to have a problem with this percent of your bolts. If we know 2% of our bolts are defective, when we send them bolts, we would say, expect this percent to be defective. So we know 2% of our bolts are defective. So 2%, yeah. So we'd say to them, well, you should expect 2%. So the person gets mad at us and they say, look. I saw 3% in my sample. Does that make sense? The person comes back to us and they say, in my sample, I saw 3%. So now we need to go to the stats people and you said 2%. We say, well, it's not always going to be 2%, right? There's variation in that. So let's go find out if that 3% is unusual, and then we'll do our other question with the same techniques. So we go to the stats person and they say, okay, if 2% are defective, that's the mean. Now we need to find Q. And so now we do P times Q over N square root. And that's going to be the standard deviation. So now it's going to be a little odd. Not technically. And I'm going to do the quick draw with the David M. Lane. What do you notice? What do you notice about 3%? It's less than what? What do you notice about 3%? This person's complaining because 3% of their bolts were defective. They said, you said 2%, but we had 3% of our bolts defected. We had 15 out of the 500 bolts. You said it'd be about 2%. It was 3%. This is unacceptable. And I'd say, well, that it can happen. I mean, that's variation for you. What do you notice very quickly about 3%? What do you notice would go above it? It would occur 5.51% times, less than 2 standard deviations. Yeah. So they might get mad and say, you told us 2%, we saw 3%. And you'd say, well, it's coming from a population where 2% are defective. Sometimes you'll get a little bit more. Sometimes you might have towards that. Now, if they got 4%, 4% is 1, 2. It does look to be 3 standard deviations. So if you did 4% over here, it'd be 0.04 minus 0.02. Oh, I messed it up. 0.04 minus 0.02. 4% would be 3.91 standard deviations. And that's super unlikely. That would only occur 7 out of 10,000 times. So if someone came back and said we had 4% defective, I'd be like, I'm so sorry. So you think it's only 1%, right? 3%, I'm like, well, that can happen. That's the variation. 4%, I'm like, I'm so sorry. Something went wrong. We must have sent you too many defective bolts. We're really sorry about that. We're going to make sure our quality is better. At 3%, I'd be like, I'm really sorry. It can happen. 3% is sort of our upper bound on what you should expect. We do expect you'll see about 2%, but 3% is towards the upper bound of what could happen. We're going to send you some replacement bolts right away. At 4%, I'm going to go talk to the people and be like, something's wrong here. It looks like they got a defective sample that they shouldn't be seeing. It is possible that they would get that, but at this point, I'm a little bit worried. Does that make sense, Jessica? Like from the manufacturing standpoint, kind of giving some application to this chapter, because this question is kind of weird on the theory. Like, I don't know how you would know the truth for the people you're going to take a poll from. Like, that doesn't make sense to me. Awesome. Like this is highly used in the industry. Like that's why I want people to be like, this chapter is important. Because what we're going to do right here is we're going to find the mean and the standard deviation. And then we're just simply going to ask, what's the probability of less than 50%? So let's find the mean and the standard deviation. P times Q over n square root. Let me find it here. I'm going to find the standard deviation right here. There we go. And now that we have the mean and we have the standard deviation, we just ask, what is the probability of seeing less than 50%? Less than 50%, once again, is because we're asking that this does not pass. This is the secret one that is harder to find because you have to understand when they say that it's defeated, that in a sample you see less than 50%. So we're asking, what is the probability that less than 50% of people vote for it? So we have to highlight the less than 50%. Jessica, does this make sense? I just don't want to do things too quickly. I found the mean, which was P. I found the standard deviation, which was P times Q over n square root. Now that I know the mean and the standard deviation, I say, what is the probability of a sample showing less than 50%? Less than 50%, because that would mean in the sample we saw it was defeated. And there's the answer down here. And if you want to do another question, just let me know. That's the solve for this one. Find those quantities, know your notation, round to 3 decimals, and do your final check and get it correct. But I like showing the application of these. Like, why would we use this? Why do we need to know this? What's the importance of this? How would we apply this? When would something be unusual? What does this tell us? Drop some more questions in the chat. We still got like 10 more minutes. We got time for another one. I need to get my next coffee. Next coffee. Next. Awesome. Thank you, Jessica. I'm hoping if anyone wants to put what they're saying, Jessica, huge shout outs. I'm just so happy we've had a lot of 201 students. During the Kahoot, people were like, I love that, you know, we have access to you. I love that we can, even though this is asynchronous, that's really meant a lot to me because I always worry about, my asynchronous students are the ones I worry about the most. Just because I don't see them, I don't have a required class with them. But it means a lot to me that people are like, hey, feel like I'm actually, you know, I have access to my teacher. That means a lot to me. Because one time, someone wrote something in a review one time? Maybe they wrote the wrong thing, but they wrote something like, I never heard from my teacher. Maybe they just reviewed the wrong class. It's reviews like that when I get my like TN Voice reviews and a review like, I never heard from my teacher. I didn't know what was going on the whole semester, blah, blah, blah. Like, I mean, I teach a lot of students, so maybe they just reviewed the wrong class. But it wasn't asynchronous also. Maybe it was I don't know. It was a while ago. There's a few reviews that stick with me in my head that I'm like, I feel bad about. Like I feel bad that the student had a bad experience. The number one review was, the most sad review for Brian was, this class was a waste of my time and money. That was about 7 years ago. That was the most damaging review to Brian's psyche. This format has made it way better than synchronous for me. Yeah, and then on the Discord too, I probably typically wouldn't ask questions in class. That's what a lot of people, that is what so many people have said about this format. That is a very common, I feel very open, because people love typing in the chat, like just to ask a question. People don't want to raise their hand in class and be like, hi, everyone look at me. Everyone just turn around and look, because I'm going to ask a question and look at me. It's not the way it goes. But this, I think, the way we feel, like the attention is on us. But when we're typing here in chat, it's just like, just conversation. It's just, you know, and then other people are typing. And the point system for being here, yes, 100 points. Charlie knows what's up. Charlie, how are you? Have you? What are you up to, Charlie? Are you on an internship? How's life going? How's summer going, Charlie? Charlie took like 201, I think, with Emory. Like, I'm not even in one of your classes, but I still like seeing my points. Yes, Charlie, let's make you. Charlie, do you want me to have a little fun with your points right here? I reset the points every once in a while, Charlie. Let's fix your points, Charlie. Yeah. Oh, well, thank you so much. I was so concerned about this class, and I think I might actually do fine. And yeah, I think I think you're doing fine. You know, that is up for you to decide. I do internship right now. I'm a staff analyst at a CPA firm. It's great. That is awesome. Shout out to Charlie right there. Charlie, you should check your points again. You're leading the way, Charlie, on points. You should check them again. And congratulations on the internship right there, Charlie. Charlie leading the way. Charlie's hours are real. His points are a little hyperinflated right now. Over 2 million points right there. His level will update soon. Hours are real, though. Sadly, I'm going to have to reset the hours. Oh my god, right there. Well, let's throw in honor of Charlie's crazy points. Let's throw another 500 points for everybody right here. Cooper wants some 5,000 points. We're throwing a 500 right there, Cooper. So, since Charlie's no longer in class, I like to have a little bit of fun with people's points who are no longer in class. No reset hours. Well, here's the problem is I've started to do where I'm tracking hours to do attendance. So in mini term, I gave them required attendance. And the R squared on it, I might even show you it. It is insane. 15 days left for jump, and then I got to get the new license. The R squared is absolutely insane. We might end with that. I'm always analyzing my students' data. I'm always trying to see what's going on and how are students doing, and trying to get a better understanding. Does this have the attendance? Yeah, we'll do some lab. Yep. I calculated it 2 different ways. And I want you to look at this. You ready? Yeah, good question, Jessica. The average for this exam is generally a little bit lower. So do remember that it's not gonna determine everything, but it's a tougher one. It's a tougher one. Oh, I think you know what this is? So the attendance old versus the attendance new is this was halfway through the semester. This was at the midterm attendance. This was or halfway through the semester. This was at the final, the attendance. You see people jumped up from 0, like people who weren't attending, and they got a little further along right here, and a bunch of people got towards the end. But what do you notice right here? Especially even if we go and can we, like, let's just look at this cluster of the people who attended. So let's go to redo automatic recalc. If I go here and grab these points, which are the people who attended generally, and we go to rows, hide, and exclude. Ooh. Really? Oh, no, we excluded the... Okay. Let's select those people. Okay, let's just take these people who've been attending and see if it holds. There we go. Wow, look at that. Wow, this is the end of the semester attendance. The end, it holds throughout pretty much. What do you notice about this quantity right here? Because I was just that is a great regression. That is so cool. 51% of the variation in current score was explained by attendance new for this group of students. And it's probably there's a bit of an outlier issue in this because it's actually higher, 70.3%. There's heteroscedasticity down here, plot thickening for the regression. So that's why I kind of wanted to zoom in on this because you got like 2 groups of students. You got the students who attend. Yeah, it's almost textbook, right? That regression right there was almost textbook, like Charlie said. Like that is a like homoscedastic, even plot throughout. And that's the group of students over here who were attending. So it's like there's almost this predictable pattern to attending. Here, let's look at this. We'll just grab and remove those. And this is what's cool about doing analysis. That's about as textbook as you can get. Actually, there's a little bit of nonlinearity to it, Charlie. Fit polynomial, and there's I guess not, because you don't see any polynomial bend. I thought I saw a bend up there. But that is about as textbook as it gets. 51% of the variation. Yeah. Kind of last half of the semester attendance. That's crazy. And if you look, you know what's really interesting? Look at where the A's begin and look at the probability of people making an A. So if you look right here and you go and do this, you reach a point where like the people making an A, and this is with bonus because we do like the 2 points on the grade and stuff. So it's like the current final score in the class. So you can get like the extra points that MuBot gives and all that stuff. So some people were doing everything, and some people get hundreds on every test. Like I'm shocked when people get hundreds on every test. Like that's insane. But still, people attending are making the better grades. It's just super interesting to me. And I saw this, and so to me, Charlie, oh, that's the redo of it. Ooh, that polynomial model is quite crazy. Let's remove the polynomial fit. That's interesting. It does like a bend right there. So when I saw this, Charlie, I realized I need to get people attending class. So like, it's not that maybe it's just people who learn want to attend or something. You can't say if you attend class, you'll do well. Maybe it's people who are focused, choose to attend class, and that's why they do well. But I was like, with 70.3% by their most recent attendance, explaining their final score in the class, I was like, I don't usually see R-squareds that high. That is a large portion of the variation in why someone does well in the class, explained by attendance. You can take other quantities here, like someone's quiz scores, and you won't see relationships like this. Like just looking at my Pearson quiz 3, I don't think we'll see that. So if you were to look at my Pearson scores from students and ask, do those explain, you're not really going to see that sort of relationship. Well, you do. What am I saying? What am I saying? Oh, it's even higher. This one's 65%, 83%. Yeah, my Pearson quizzes actually really do explain a lot. And it's interesting because now we get into the idea of multicollinearity. Because if my Pearson quizzes explain 83%, like quiz group 3 explains 83% of your final grade, and quiz group 2 explains 83% of your final grade, how can two things explain 83%? And that's the idea of multicollinearity. Now I want to do a stepwise regression. This just leads me to so many more questions. People have no idea how much I could just sit down and analyze this data, which I do. I just want to go through and understand. Okay, let's try this. Okay, whoops, I didn't do the stepwise. Okay. So let's find out. Attendance new came in. Good, I like that. Attendance and quizzes. No Canvas content? Wow. This now explains, where's my R-squared? 95% of your grade. Your attendance and doing quizzes. Attend class, do the work. Attend class, do the work. 95% of your grade. 95% of your grade. There's the regression model right here. And look at how close right now, Charlie, look at this. This looks a lot more textbook, doesn't it? How the even scatter, the good residuals, attend class, do the work. And there's the residuals right there, which look pretty clean, pretty evenly spaced. It's not really heteroscedastic. It's just because there's 1 point down there. So we do see kind of a general spread pattern. The error ribbon is thin, though. Yeah, so that's good, though. Well, so this is the prediction interval for an individual. We do see people escaping outside the prediction interval. Or is that no, it's the confidence interval for the mean of the line. I think that's the confidence interval for the mean of the line. I do it in R usually, as you know. What's even cooler about this is you can go down here to factor profiling, and I can actually make predictions. So I can actually go to a student and say, like, if your attendance, like we could say, like, if you do all the work but don't attend class, you are predicted to make an 82. If you do all the work but don't attend class, you'd be predicted to make an 82 with a low prediction of 76, and those are confidence intervals right there. So if a student were to do all the work but not attend class, what if they only do B work but attend class all the time? So now let's say a student does B work and attends class all the time. It's still it'd still do decent. It'd make a C. You'd probably make about a C. You see the errors right there. But now if you start doing more work, whoop, your grade starts going up. It's interesting. There's a negative relationship right there. That can happen. Does that have a negative coefficient? Looks like it does. It brought in this to lower the AIC. It looks like quiz group 2 is being weird. But yeah, that lowers the AIC. It's got a negative coefficient. Ah! But so many cool things right here. This is what I love talking about and thinking about. You can see the negative coefficient right here, which is weird to think that quiz 2, but it's just the way Charlie probably knows about AIC. We won't teach about AIC right now, but this optimized based on AIC, or did it optimize on BIC? I think you choose in the model platform. When you run stepwise, there's the AIC. Minimize BIC, minimize AICC. So that's Akaike's corrected criteria right there. So if I were to minimize, BIC is basically the same as the Bayesian information criteria, but just understanding what this is doing, p-value threshold, so it's going to bring things in based on p-value being statistically significant or not. But no, this is super cool. Jump's got some pretty good stuff on this, and this is stepwise regression, something we cover in 320. We cover stepwise regression. With that, a lot more to talk about, a lot more to do. Building models, trying to explain data, trying to understand what's going on. And we see that doing the MyPearson work, coming to class is super important. So do the work, come to class, and you'll probably make a good grade. But sometimes you get one of those residuals that's a little bit further off than you would like. Hopefully it's a positive residual, not a negative residual. With that, we'll see everyone later. Bye for now, everyone. Bye.